So let's continue with our considering of FM in noise. We started by a signal that had a single parasitic unmodulated carrier, 2 pi FCT plus UN cosine 2 pi FC plus Fn T. And then after some mathematical manipulations, we discovered that this signal can be approximately written as 1 plus UN over A C cosine 2 pi Fn T, and then cosine 2 pi FCT plus UN over AC sine of 2 pi Fn T. So that's what happens when you have a small parasitic component right in the vicinity of the carrier. What you look at this and you say, oh my God, what happened here is the parasitic component caused this signal to be modulated both in the amplitude and in phase. If you look at the nature of the amplitude modulation, this is double sideband, large carrier, right? You wouldn't think it would surface up here, but it does surface up here in FM. And this is our angle modulation, which we can interpret as a phase, but since we're going to present this to a frequency demodulator, the frequency demodulator is going to assume that this is a frequency modulated signal, so it will interpret this as a modulation part, frequency modulation part that it actually cares about. Now, this signal is going to be presented to FM demodulator. FM demodulator, if you remember, when we didn't have noise, we presented this to a filter that had, we converted this signal from FM modulated into AM modulated and then passed that to the envelope detector. The filter that translates this signal from FM modulated signal into AM modulator, we called it discriminating, right? It was that filter that had a linear magnitude response as a function of frequency. The simplest form of discriminator was a differentiator because, you know, just J omega is a linear function of frequency. Here, now that I have noise, I realize that I have these amplitude variations that I know are not from the signal. They are coming from the noise because signal did not modulate the amplitude. Remember, when you modulate FM signal, it comes with a constant amplitude. So, because I know that, here's the how my FM receiver looks like. Just like in all our systems, there will be our good old friend, front-end filter. What is the bandwidth of this one going to be? If my signal has a bandwidth of W and beta was used for modulation index. 2W times 1 plus beta, right? That's what the bandwidth of this one is going to be. 2, 1 plus beta times W, right? Where W is the highest frequency in the spectrum of my signal. Now, we know that this is Carson's rule. This is the bandwidth of our FM signal. And we want this filter to be as tight as possible, right? Just let my signal go through, get everything else is noise. Now, the next component is new. It's a component that we call limiter. And I'll have to explain the function of that component here. And then you're going to have FM demodulator, followed by our low pass, the DC blocking circuit. Actually, sorry, I forgot one. There's going to be, at the end, a low pass filter. What's going to be the bandwidth of this one? 2W or just W. This is at the basement. Just let my signal go through. And this is a DC blocking. Right? That will block the DC component. So this is signal Z1 of T. I'm going to call this signal Z2 of T. And I'm going to call this Y. Okay? And what I'm going to do is I'm going to present this signal to this structure here. Now, this signal is going to appear at this point. What does the limiter do to its signal? Let me just give you a big picture and I'll talk about how you implement this guy. The limiter looks at this signal and if I were a limiter, I'm going to say, forget about this stuff. I know this comes from noise. Let's take these variations in the amplitude domain and remove them. They're not carrying any information. So just replace this whole thing with a constant term. Right? Now, how do you do that using electronics? Limiter is a combination of two things. It's a combination of a clipping circuit or a nonlinear amplifier and appropriate filter. So, what does how does the limiter implementation? It is going to be a clipping circuit, that clipping amplifier, that will look like this, and then I will follow this by a bandpass filter with a proper frequency FC. Right? Now, why does this work? Okay, let me try to sketch what is happening here. This is my limiter. This is in. This is up. These transfer characteristics, and it looks like this. So, if your signal is in this range from here to here, then the input is equal to output. If your signal starts going outside of this range, it's clipped. Just, clipped to that level, to the maximum level, right? So now, let me present to this element here. Let me present a sinusoidal that has an amplitude that is modulated, slightly, right? Slightly modulated amplitude. So let's say sinusoidal that with a peak amplitude here, that kind of looks like this. So it's a little bit over, a little bit under here, a little bit under, a little bit over. What is it that I'm drawing? I'm essentially drawing this, right? I'm having a sinusoidal. I'm not very good in drawing. You think of this as T-x is this way and Y-x is this way a little bit. But you can see that the amplitude here is modulated, right? It kind of goes up and down. But it's outside the range, right? So now, let's look at what happens when you clip it. What comes at the output here is this. You have your sinusoidal that was like this before, whatever these variations were, but it's now clipped, so it's like this. Okay? You see what happened? It's now forcing the amplitude to be the same. It used to be, it's not sinusoidal anymore, but it's a clipped waveform with a constant amplitude, right? Now, you guys are experienced enough. When you look at this, what do you see? You see periodic waveform that implies Fourier series. What's the fundamental component of this Fourier series? It's the same frequency as this sinusoidal, right? That's the fundamental frequency of this, right? And then you have second harmonic, third harmonic, and so on. So if I follow this with a filter that is centered at FC and rejects all the higher order harmonics, what comes out here? In unmodulated sinusoidal, right? Let me walk you through this again. You have a sinusoidal that's modulated in the amplitude, right? Now you clip it at its high. What you end up is with something with a square waveform that has a constant amplitude, right? Now if you look at this clipped waveform with the Fourier series glasses, you have a whole bunch of harmonics, an integer multiple of the fundamental. Fundamental is the same, it's this frequency of this guy. So by tuning this filter to a fundamental, all you get is cleaned up sinusoidal, the one that now has the same frequency but not very amplitude. That's what limiter does. So if you put this through a limiter, what will happen is all of these variations are going to go away. Right? You're going to actually end up with a sinusoidal that just has these modulations in the frequency. Okay? Right. So I guess limiter, conclusion here, limiter eliminates amplitude variations. So, after limiter, I get my signal Z1 of t. Let's write the expression for Z1 of t. So Z1 of t is going to have now constant magnitude, which I'm going to call m, cosine 2 pi fct plus un over a sine 2 pi fn. Okay? Now, I'm feeding this into FM demodulator. What does FM demodulator do? It generates the signal that's proportional to the instantaneous frequency, right? So my output signal Z2 of t is going to be something proportional to the instantaneous frequency, because it's understood, this receiver understands this is an FM modulated signal. Now instantaneous frequency is 1 over 2 pi derivative over time of your instantaneous phase, right? Which in our case, this is 1 over 2 pi derivative over time of 2 pi fct plus un over ac here, sorry. ac sine 2 pi fnt. Okay? Now when you take the derivative, you can see this 2 pi and 2 pi cancels. I have fc plus 1 over 2 pi times un over ac. Derivative of the sine is cosine, so I have 2 pi fn times cosine 2 pi fn t. And when I tidy this up a little bit, I get fc, 2 pi cancels, plus un fn over ac times cosine 2 pi fn t. So that's my Z2 of t after demodulation. And then this guy goes through a low-pass filter. So if this Fn is within a band allocated to my signal, it will go through. Both of these will go through. And then finally, the DC blocking circuit will get rid of this piece here. So you're going to have that Y of t is going to be Un Fn AC times cosine 2 pi. So this is what shows at the output all the FM received. So I took my signal, corrupted it with the parasitic component here, and then this is kind of a little bit under assumption that this component is small. This is a good approximation. I took this signal, presented it to the FM receiver, and what came out is this parasitic component piece showed at the output, right? It is at a frequency that is the offset between the parasitic component and the carrier. But there is a very interesting thing here, is that its magnitude is multiplied by the frequency. So if your Fn, your offset is small, this component has a small magnitude. If your offset is larger, the magnitude of the component gets amplified, right? Very strange thing, right? So the components that are close to your carrier, that corrupt the carrier, are not going to be of as big of an amplitude at the output as the one that are further away, right? we're going to come back to that. This is very important assumption. But from right now, let me summarize graphically what we have analyzed. So here's our starting point. This is your carrier. It's a strong sinusoidal that has magnitude proportional to the AC. There's a parasitic component here that has the magnitude UN that's separated Fn in the spectral domain, right? That's what is presenting an input. And what I get at the output is now I'm looking at the baseband. This is carrier is moved to 0. And this component now appears at the baseband. And it has a magnitude UN times Fn over AC. The magnitude of this component will depend on its frequency. So the closer it is, the smaller it's going to be. Right? If it's over here, it's going to be larger. And then it is inversely proportional to AC. So the larger AC relative to the UN, the smaller this corruption is. You know, in FM, once your carrier is strong enough, then your noise tends to disappear rather quickly. Okay? So that's the first easiest case that we could consider, right? So let me, because this is a tail end of the lecture from the last time, let me give you the homework. This is homework number 12, according to my records here. Exercises 8.1, 8.2, 8.3, 8.5, and 8.8. And then assignment none, right? Don't have an assignment, just do these exercise problems. They would help you understand better than nothing so far. So that was the first step. Let's take the second step. The second step is going to be, instead of having just a single component, I'm going to corrupt with multiple components, see what happens. And then eventually I'm going to put the noise, which is continuous. So here my signal is unmodulated carrier plus sum of parasitic components with a sum of parasitic components. So here my signal R of t, it looks like this: AC cosine 2 pi FCT plus sum, when k goes from 1 through m, u and k cosine 2 pi fc plus fnk t. Right? I have a whole bunch of, and I can put here theta k, because now that I have many of them, I cannot hope that they're all of the same phase. Okay? So I have my carrier, and then I have a whole bunch of components corrupting it. This is what the picture is. There's a carrier, and look at them here. All of these small parasitic components corrupting this carrier. And you can see how this is closer to the noise than the previous component, the previous step, right? These carriers are here, and if you go a little bit further and you kind of squint, they kind of merge into the noise flow. And that's what we're going to do in the third step. All right, so this is F, this is your AC, and this is U and K. Right? All of these, where K goes 1, 2, 3, however many you want to put there. So we rewrite this R of t as AC plus sum when k goes from 1 through m UNK cosine 2 pi FNK t plus theta k. That's the first term times the cosine 2 pi FCT and plus sum when k goes from 1 through m UNK times sine of 2 pi f n k t plus theta k. This thing times sine of 2 pi f c t. Alright, what did I do? The same thing I always do. We group the things that come with the cosine of the carrier, group the things that come with the sine of the carrier, and then we can use that identity. Now, we all know that this is now m of t times cosine 2 pi fct plus some psi of t, right? Where m of t is this whole thing squared plus this thing squared, take a square root, and this psi of t is arctangent of this over these two. Now, m of t I'm not going to worry about. Why is it that I'm not going to worry about it? Because I know what happens. I present this to a discriminator. Discriminator gets rid of all the variations and replaces m of t with a single sinusoid, single amplitude, right? So, so I guess let me put here again the structure of my receiver. Here's my front end filter. Here's my limiter here. And then here I have an FM demodulator. And then here I have this DC block circuit. So here's R of t. Here's a signal that I'm going to call Z1 of t. And here's the signal I'm going to call Z2 of t. And there's my output Y of t. So that's my receiver. So this is FM receiver. It's easy to write Z1 of t right away. Z1 of t is going to be some constant magnitude. I'm just going to say A cosine 2 pi fct plus psi of t. A is constant because this limiter here eliminates all the variations in this m of t. The psi of t is arctangent of whatever I have here divided by whatever I have here. Actually, let me just do minus here so that we're, oh no, you should have corrected it. What should be here? What is here? Is it plus? Minus, right? Cosine alpha plus beta, cosine alpha, cosine beta, minus sine alpha, sine. So this should be minus. So then it's plus here, right? Because of that. So the arctangent of sum of UNK sine of 2 pi FNK t plus theta k over k. K goes from 1 to n. And downstairs I have AC plus sum when k goes from 1 to n UNK cosine 2 pi FNK t plus theta k. So that's my modulated by angle. Now, under the assumption of high signal to interference ratio, your AC is much greater than this thing. So AC is much greater than sum k goes from 1 to n UNK cosine 2 pi FNK e plus theta k. So under this assumption, you can neglect this whole summation relative to the AC. AC comes inside, this whole term upstairs is small, so arctangent of something small is whatever that small is. So your phi of t approximately becomes sum when k goes from 1 to m unk over ac times cosine, sine of 2 pi fnk t plus theta k. So that's your phi of t, right? In the expression of the signal z2 of t. So z2 of t is, z1 of t is this, and then phi of t is essentially this piece here. Now, z2 of t, what is z2 of t proportional to? It's an FM demodulator, therefore z2 of t is proportional to instantaneous frequency of your signal, right? We have to determine what instantaneous frequency is, and that's essentially your signal z2 of t. So, z2 of t is proportional to, all right, let me just say equal. So 1 over 2 pi derivative of whatever is the argument in a z1 of t. But the argument in z1 of t is 2 pi fct plus sum when k goes from 1 through m unk over ac times sine of 2 pi fnt plus theta k. That's what z2 of t is going to be. It's going to be instantaneous frequency. Instantaneous frequency is 1 over 2 pi derivative of instantaneous phase. And this is instantaneous phase. Now this is easy to take the derivative, so this is fc plus sum when k goes from 1 through m unk times fnk divided by ac times cosine 2 pi fnt plus theta k. And then after we block the DC component, because of this circuit here, then y of t is just going to eliminate fc, and therefore y of t is going to be sum k goes from 1 through m unk fnk divided by ac times cosine 2 pi fnt plus theta. Okay, so that's the output. We kind of follow the same path we did for a single component, and we found out really strange thing here, and that's not strange when you think about it a little bit, but we talked about FM as nonlinear modulated system, yet there's it almost seems like an evidence of a superposition here, right? We saw that we have some of the sinusoidals at the input, there's a sum of sinusoidals at the output. Now, why is that the case? Well, even if the system is nonlinear, for the small disturbances, it can be linearized locally. And that's what we are doing here. We're saying, well, these guys are small in magnitude, therefore even the demodulation is nonlinear. You know, if I'm in a small range, every nonlinear function can be expressed as a linear function, right? So therefore we have something close to superposition here. But here's the big picture. This is what you need to understand. Let's look at what happens here in a... This is your carrier, right? This is at the carrier frequency, at the carrier. There's a carrier AC. There's these, let's say, 3 small parasitic components. This one is Fn1. Let's say they have the same magnitude, UN1, UN2, UN3, but they have different frequencies. This is plus Fn1, plus Fn2, plus Fn3, where the plus here refers to the carrier frequency. So this is the carrier frequency. The frequency of this guy is whatever is the carrier frequency plus Fn1. The frequency of this one is carrier frequency plus Fn2, and so on, right? You have 3 of them. Now, if you bring this all the way to the baseband, what happens? The carrier was brought to the origin, right? But it was eliminated by the DC blocking circuit, right? Carrier contributes to a DC component, so it's gone. Now, that's this guy at 0. And then there are 3 components here. One is Fn1, Fn2, Fn3. What happened to their magnitudes? Their magnitudes are scaled by Fn. The further away they are, the larger their magnitudes are. See, the first one has a magnitude UN1 times Fn1 divided by AC. Right? It started as UN1, now it's UN1 over AC times Fn1, right? Where F is it's offset from the frequency of the carrier. The last one has the magnitude UN3 times Fn3 divided by AC. So the last one has the largest magnitude. Why? Because its offset from the carrier is the largest. Okay? So the translation here, yes, they translate to the baseband, but in the process of the translation, they're not amplified by the same amount. The ones that are close to the carrier are amplified less. The ones that are far away from the carrier are amplified more. Any questions here? All right. So let's now look at the general case, FM signal in white noise. So FM signal in white noise. Here's what we're dealing with. F, here's our carrier. This one is the frequency FC. And this is FMK. Okay? Now, look at all of these components. Okay? They're small in magnitude. They're separated by delta F, small incremental frequency. And they have their magnitudes here are delta U and K, right? The small magnitudes in the amplitude domain. Now, this FM carrier goes through a front-end filter. Front-end filter is going to get rid of some of these guys. The bandwidth of this thing is going to be 2 times 1 plus beta times W, right? That's going to be the bandwidth of your front-end filter. So it's going to let some of these guys go through. It's going to reject a whole bunch of them, right? So consider a single one of these guys. Let's say this guy here. What happens when you present this one to the FM demodulator? There will be a component that corresponds to this one at the baseband, right? That component, according to this, is going to be at a frequency equal to the offset, and it's going to have a magnitude divided by the magnitude of the carrier, right? So if you look at this one, we'll generate a component in the output. That will have delta U and K at the output. Is going to be some constant here, K, times the value of this delta U and K divided by S AC times F and K. That's going to be the magnitude at the baseband that corresponds to this one. Okay? That's the magnitude. If I take both sides of this, I square it and divide by 2, what is it that I'm getting? if I look at 1/2 of delta UNK and the output squared, what is this? It's the power of this component, right? This power of this component at the output. And this power is going to be k squared delta UNK squared divided by AC squared times FNK squared. Now, this is power. And I'm missing 2 here, right? So let me put 2. So I can now say power of the k component of the noise and the output is going to be 1/2 k squared Fn k squared divided by AC squared over 2 times the power of the component, the same component at the input. Just this P and K is the power, P and K is the power of this component. So the power of this component at the input and the power of the same component at the output are related through this expression here, right? And how did I get to this expression? Well, I know how their magnitudes are related. By squaring the magnitude and dividing it by 2, I get the power. So I get that the power at the output that is contributed to this noise component is whatever is the power at the input times this scaling factor here. I'm going to write this scaling factor as 1/2 k squared times Fnk squared, and then I'll write this as Pnk divided by S, where S is going to be AC squared over 2. And that's my power of the K. Right, so that's this S, power of the K, right? So the power of the output NK component is going to be whatever is the power of the corresponding input component divided by the power of the carrier, and then times this scaling factor that maps between the two. And now we're almost there. So there's just a couple of lines, and then we'll actually finish this journey and then start utilizing this to derive that signal to noise relationship. Now, let delta F go to 0, delta UNK go to 0, but in such manner that delta UNK over delta F go to some and 0, right? What is it that I'm saying? Let the separation between these components become ever smaller. So essentially I swipe the entire axis. Let their amplitudes become smaller, but in such manner that their power spectral, that their, over 2, that their power spectral density, power over frequency, converges to a constant power spectral density. So what is it that I'm making this process go to? I'm making these discrete sinusoidals eventually converge to a continuous spectral representation of the white noise, right? I'm letting their separation go to 0, their magnitudes, individual magnitudes go to 0, but their power spectral density eventually becomes constant, which is my model of the thermal noise. So if that's the case, then that relationship for the power, I can say the element of the power at the output is going to be 1/2 k squared f squared, the element of the power at the input divided by the k. If I divide both sides of this by f, then I get d pn by delta f, sorry, over df is equal to 1/2 k squared f squared dp and input divided by df divided by power of the k. Now, element of the power divided by element of the frequency, what is this? Power spectral density, right? So this is watts per hertz. How many, what is the power spectral density at the output? So this is PSD at the output. And this thing here is the PSD at the input. So I get beautiful relationship here that says this Sn output of F is going to be equal to 1/2 k squared F squared divided by S times the Sn output of F. Oh, sorry, input. This is input. So this tells me how does the FM demodulator change the power spectral density of the noise. In all other demodulators that we faced so far, the noise was just translated to baseband. So the power spectral density, except maybe amplitude changes, didn't change in shape. Here we have a qualitative difference. Well, there's this factor here that shapes the power spectral density. So what starts as a constant here, as a function of frequency, is not a constant as a function of frequency when it comes to the output. I think I give a little drawing here. So in our case, let me just write the expression again. In our case, in this case, our Sni of F is equal to N0 over 2 for every F, right? Or N0 if you want to look at it a single side there. Well, let me just say N0 because I have it. That's what I use in notes. So your Sn output of F is going to be 1/2 k squared F squared over S times N0. So that's our power spectral density at the output. Let's take a look at what does that mean. Here's our power spectral density at the input. It's N0 over 2. That's our white noise, right? This is what we feed into the FM receiver. What FM receiver does with it is this. Right? So this is equal to S and input of F. S and output of F is going to be k squared, that's some constant associated with a demodulator, times F squared over S times N0 2. And now what happens is, if my signal extends up to W, the noise that is captured at the output is this. The power spectral density of the noise changed. It's not flat anymore. The noise is now what we call color noise. It has a color. It is not white. White means with a uniform power spectral density. Color noise means that noise that has a non-uniform power spectral density. Now we have everything we need. If we still remember what is it that we're trying to achieve. Do we still remember?
Okay.
What is it that we're after? Mapping between signal to noise at the input and signal to noise at the output, right? This is the big picture, right? But why did we need to do all of this? Because we didn't know how the noise travels through the FM receiver. We understand how the signal travels. We talked about that before, how you demodulate. You do discriminate and then you filter at the baseband. but we didn't know what happens to the noise. Now we understand what happens to the noise. Noise goes in as a white noise and comes out as a colored noise. It starts as something that has power spectral density N0/2 and comes out as something that has power spectral density proportional to the square of the frequency. Right? So let's now calculate the relationship between signal to noise ratios at the input and the output. So signal to noise relationships. Okay, let's first start at the signal to noise ratio at the input. We know it's a power of UFM of t, my modulated signal, divided by the power of the noise. Power of the modulated signal. If this is a FM carrier, does it matter that the signal is modulated? For FM carrier, the power of the modulated signal is the same as the power of the carrier. Remember, that was for the midterm exam, right? Because you're modulating only the phase, and power depends only on magnitude, the power does not change as a function of the modulation, right? Your power is always going to be AC squared over 2. So the power of the FM signal is AC squared over 2. How about the power of the noise at the input? Well, it's going to be N0 times the bandwidth over which you're operating. That power is dictated by whatever is the front end of your filter, right? Well, this simplifies as AC squared over 2. This is N0. What is the bandwidth? 2 times 1 plus beta times W. So your signal to noise ratio at the input is going to be AC squared divided by 4, 1 plus beta, and 0 times W. Okay? So that's the signal to noise ratio at the input. How about signal to noise ratio at the output? Signal to noise ratio at the output is going to be power of the signal, whatever is the signal piece of the output, divided by the power of the noise and the output. Right? Now, power of the signal. So to determine what the power of the signal and power of the noise at the output, let's look at what our UFM of t looks like. It is AC cosine 2 pi FCT plus 2 pi KF integral from minus infinity to t m of tau d tau. Right, this is our general expression normalized here for the FM modulated signal. What is the here S of t? S of t is what comes at the output, and it's going to be again proportional to the instantaneous frequency of the signal here. So it's going to be 1 over 2 pi derivative with respect to t of minus the DC component, right? So let me just do this. It's just going to be 1 over 2 pi derivative with respect to t of this piece, because this one will give me DC that will be eliminated anyway. So it's 2 pi kf times integral from minus infinity to t and normalized of tau. And this 2 pi and 2 pi cancel, so it's going to be kf times m of t. But we like to express this in terms of beta, and it's going to be proportional somehow. Let me put some k here, because I put the k Did I put the, yeah, I put the K here. That's the same K as the one. So now, we like to express this in terms of beta. So I'm gonna now write this as K, and Kf can be expressed as, remember our definition of beta for Fn was delta F maximum over W, right? So delta F maximum is going to be Kf times the maximum of this guy, right? So I can write this whole thing as K times beta times W divided by maximum of M of T times M of T. In a sense, making this normalized signal. So I can write this as K beta times W times M of T. Right. So let's just look at where is this coming from. Delta F maximum is going to be whatever is the Kf times maximum of M of T, right? And then I divide this by W. Now if you look at here, now if I express Kf from this here, it's W times beta divided by this. And this is exactly what I put here, right? So, I mean, it's kind of like just manipulating formulas, but let me just, this is how we define beta in FM modulated systems. So I'm looking at what is the delta F maximum. It is whatever is this Kf times the maximum of M of T. But, and then W is coming from here. So if I use now this expression here, I can express this Kf in terms of beta. And the Kf in terms of beta is W times beta divided by maximum of the magnitude of T. And this is exactly what I have here. So it's K times what used to be Kf, now expressed in terms of beta, times M of T. But M of T divided by maximum magnitude of M of T, this is what we call normalized M of T. So that's what I have. So that's what the output signal is. Now what is the power of this signal? Power of S of T. I'm going to take the square of this and average over time. So this is K squared times beta squared times W squared times massive normalized of T squared or average over time. Or the shorthand notation K squared times beta squared times W squared times power of message normalized. Say again? So that's the power of the signal. Now the key thing is that justifies all the things that we did before is now power of the noise at the output. And I'm going to say this is integral from minus W to plus W S of the noise at the output of F dF, right? What am I doing? I'm actually determining the power of the noise by integrating under the power spectral density of the noise at the output. So all I need to do is now substitute what the power spectral density for the noise at the output is and get the power. So this is going to be 2 times integral from 0 to W K squared F squared over S times N0 over W. Where is the 2 coming from? I'm integrating, the function is even, so I'm integrating on the right-hand side home. So if I now, of course there's dF, right? So let's take everything out that does not depend on F. Obviously K squared goes out, S goes out, N0, these 2 and 2 cancels. So I have K squared N0 over S. Integral from 0 to W of F squared is going to be F cubed over 3. right? So it's f cubed over 3 from 0 to W. So I get interesting result, k squared and 0 over s times W cubed over 3. So that's the power of the noise at the output. Make sure I didn't forget some. Okay, so that's that. I can bring back what this, since I have AC squared here, let me replace S with the same thing. So it's k squared and 0 times W cubed over 3 times AC squared over 2. AC squared over 2. Now I have everything. So signal to noise ratio, the output, is going to be whatever is the signal, so it's this stuff here, k squared, beta squared, W squared, power of the message normalized, divided by whatever is the noise at the output, which is k squared and 0 times W cubed divided by 3a squared over 2. And you can see that some of these things will clean up. So you end up with a signal to noise ratio at the output as being, let's see here, k squared, k goes away, right? So k and k cancels. This W squared and W cubed cancels, so I'm left with a W downstairs. And this 3a squared over c goes upstairs, so I have 3 beta squared, p message normalized. Downstairs I'm left with n0 times W, and then I have a squared over ac squared over 2 here as the last term. Okay? Now I have signal to noise output, I have signal to noise input. Both of them have AC squared over 2. So let me express AC squared over 2 from the first one. So I'm going to designate this as a star. So from star, signal to noise ratio, or I should say AC squared over 2 is going to be equal to 2 1 plus beta times n0 times W times signal to noise ratio at the input. And now I put this in this expression here, and I get something that looks like this. Signal to noise ratio at the output is going to be equal to 3 times 1 plus beta times beta squared times 2 power of the message normal divided, no, I don't have anything divided because you can see this cancels with this, and then I have just signal to noise ratio at the end. Okay, that's the end of our journey, right? Look at this. I'll just stop for a second, let you people that are writing finish writing, because I want to play, big importance to the next few statements I'm going to make. Remember, some time ago, I promised you, we have to justify why in the world we use FM. It was really tough, right? It's tough to modulate, it's tough to demodulate. It has a broad bandwidth, right? Why do we use it? Here's the payback. This is your output signal to noise ratio. What is this? This is an input, output. What is this? Processing gain. So this is our processing gain. Let's assume that we are modulating with sinusoidal. So what is the normalized power of the sinusoid? What's the power of sinusoid? 1/2, right? So this is 1, okay? Let's say we use beta. What's the typical value for beta? Let's say 5, right? So put 5 in here. 5 squared, 25. Times 6. 6 times 20, 120. 6 times 5, 30. So 150. Times 3. 450. So how large is improvement in signal to noise ratio? 450. Right? What was it in a double sideband suppressed carrier? 2. What was it in single sideband? 1. What was it in a conventional double sideband large carrier? It was smaller than 1, right? We just send carrier, right? And a little bit of signal, but it's mostly carrier, right? 90% of it's carrier. Here, my receiver processing is 450. So my signal is 450 times better signal to noise ratio when it comes to the output than what it was at the input. So it's tremendous, right? If you give me a signal that is above certain threshold, my noise is beat up by the receiver, right? It completely rejects everything. It improves my performance many dBs, hundreds of times. That's the reason why we use FM. And you know that. What's the clarity of the FM radio? It's gorgeous, right?
The quality of sound.
Quality is excellent. Wherever, and you know, some of you guys been in our RF propagation, you know how an RF signal bounces back and forth and stuff, and there's all sorts of fading and noise. Do you hear that when you're driving around? No. It's clear, right? It's as long as you're within the coverage of the FM radio station, it sounds great. But what happens is you start exiting the coverage of the FM radio station? It deteriorates really fast. As a matter of fact, once it starts deteriorating, it's so unpleasant, you immediately switch the radio station. You cannot listen. If you ever try to listen to AM, sometimes it's noisy, but it's not unpleasant, right? You know, it kind of degrades slowly. But FM, the moment it starts degrading, you hear all of these very high frequency, annoying signals, right? And you just have to switch the radio station. You cannot listen to poor FM. It's either clear or it's unlistenable. Right? And we explained the clear part so far. I mean, I just gave you the explanation using this expression. We'll use it more to kind of get a better feel. But we are still to explain this other part, why you cannot listen to bad FM. Why does it deteriorate so fast? So, in a nutshell, this is a justification for using of FM. Because your receiver is capable of beating down the noise tremendously. Your processing gain is on the order of hundreds, 20, 30 dB, right? Between 20 and 30 dB. Now, this expression is not given in your book. I don't know, the author is kind of, he's referencing everything to N0W. But the equation he gives is the same one as I have here. It's just disguised a little bit. So just since you're, I hope, I know you guys are reading the book, so let me anchor this to the same equation in the book, right? In the book, he gives you this equation. He starts from here, and then he says other way or right. We can say that signal to noise ratio at the output is going to be 6 beta squared, 1 plus, no, just 3, sorry, I have 6, 3 beta squared, 1 plus beta, so I'm copying this part here. And then I put 2 power of the message normalized, this guy. And then instead of signal to noise input, I write what I have over there, right? AC squared over 2 divided by N0 2 times 1 plus beta times W. Okay? And now, if you cancel some things, this 2 and 2 will cancel, and this 1 plus beta and this 1 plus beta cancels, and you end up with the expression 3 beta squared power of the message normalized times AC squared over 2 over N0 W. So that's an expression that he has in the book. This is the equation 5, 3, 24. It's the same equation as this one, but I find this one much more, you know, telling, right? Much more, I guess, insightful. One thing that this one is, where this one is deceiving, is if you look at this one, it seems like you're gaining a lot by increasing the beta. It seems like the signal to noise ratio here at the output is the signal to noise ratio of input times beta cubed, right? So that the improvements are on the order of beta cubed, you know, and this is what kind of I have here. If beta was 5, then beta cubed is 125 times 3, that's that improvement we're talking about. The situation is a little bit different, because what you don't see here is as you increase in this equation is that as you increase the beta, your bandwidth increases linearly with beta. Therefore, your processing gain goes as a beta cubed, but your input signal to noise ratio decreases as 1 over beta. So the overall improvement is kind of better seen in this one, where you can see that your overall improvement is beta squared. Right? So that's more insightful from that perspective, right? How fast you grow as a function of beta. But I want you to kind of put this one handy. We're going to use it in a lot of problems, and that's the one that justifies the use of the FM. Okay. So I think we have completed that original task, that was to derive that functional relationship between signal to noise at the input and signal to noise at the output for all modulation schemes that we used. Next time when we come, I'm going to just give some examples of this, and then we'll also address one thing that you see here, that your noise in the output is not treating all the components of the signals equally. It is affecting the ones that are at the very end in much more. Right? So we need to address that, and you will see there is an additional, 10 to 15 dB of improvement, right? When you start doing this. So we're talking now from a couple of dBs, we're going to 20, 30, 40 dB of improvement from processing. Okay, so that's going to be next time.